Welcome to Jeremy's IT Lab. This is a complete course for the CCNP ENCOR Enterprise Core exam. In this video, we'll examine how switches running MSTP interact with switches running PVST+ or Rapid PVST+. Ideally, all switches in the LAN will run the same version of STP, but it's important to know how switches running different versions interact. Here's what we'll cover in this video. First, I'll give a general overview of connecting MST regions to PVST+ or Rapid PVST+ domains. By a PVST+ domain, I mean one or more switches that run PVST+. Then we'll examine the PVST simulation mechanism that Cisco switches running MSTP use to interact with switches running PVST+. We'll cover two main scenarios, each with different considerations. First, we'll see what happens when the CIST root is in an MST region. And then we'll see what happens when the CIST root is in the PVST+ domain. Before we get started, here's a brief summary of the key points in this video. Cisco switches running MSTP can interact with switches running PVST+ through the PVST simulation mechanism. There are two main points here. When receiving BPDUs from a PVST+ switch, the MSTP switch maps the VLAN 1 BPDU to MSTI 0. Only the VLAN 1 BPDU. The others are not used to determine the topology. And when sending BPDUs to a PVST+ switch, the MSTI 0 BPDU is duplicated and sent in each VLAN necessary, each VLAN that the PVST+ switch runs. As we covered in the previous videos, only MSTI 0 is used when interacting with switches outside of the MST domain. This means that each MSTP boundary port, a port that connects to a PVST+ switch, is either forwarding in all VLANs or discarding in all VLANs. They can't maintain a separate state for different VLANs. And this necessitates a couple of rules that must be followed to avoid loops in the LAN. Okay, these are some of the key points we'll cover. Let's get started. First, let's look at the MST region we'll be using, the same one we used in the past couple of videos. Here is each switch's priority in each instance. The MSTI 0 priority is most significant because it's the only instance that interacts with switches outside of the region, whether they're switches in another MST region or switches running PVST+. I configure the name region 123 and revision number 1. As a reminder, this revision number isn't really necessary. It's just a number you can optionally configure that has to match among the switches in a region. The name is technically optional too, but I think it's a good idea to configure it. Our example LAN uses VLANs 1 to 100, so I mapped half of them to instance 1, where switch 1 is the root bridge, and half of them to instance 2, where switch 2 is the root bridge. And here are the settings we just configured. Finally, here is the role of each switch port. Now let's connect a PVST+ switch to this region and see what happens. I've added switch 4, a switch running Rapid PVST+ with VLANs 1 to 50, to the LAN. Notice it has the default priority in each VLAN, 32768 plus the VLAN ID. Now let's connect it to switch 2 and switch 3. Before we dig into any details, let's see the status of the LAN after connecting switch 4. Here's Show Spanning Tree MST 0 on switch 2. Take a look at its G02 port. A port connected to a non-MSTP switch is always considered a boundary port, as indicated by bound here. In the previous lecture video, when we looked at connecting different MST regions together, I defined a boundary port as a port connected to a link in a different region. And a link is in the region of the link's designated bridge, which is switch 2 in this case. So using that definition, G02 wouldn't be a boundary port. But it's different when connecting to switches that don't run MSTP. All ports connected to non-MSTP switches are boundary ports. PVST, in parentheses, means the PVST simulation mechanism is running on the port. This allows switch 2 to interact with switch 4 in a way switch 4 understands. We'll explore how PVST simulation works throughout the rest of this video. Now let's take a look at the output of Show Spanning Tree VLAN 1 on switch 4. It's running VLANs 1 to 50, but the output will be the same for all instances. First, notice that switch 4 is running Rapid PVST+. The PVST simulation mechanism works identically, whether the non-MSTP switch is running PVST Plus or rapid PVST Plus. So throughout this video, I will just refer to it as PVST Plus. Now let's look at this output for switch 4's two interfaces. Pure STP means the port is connected to a neighbor using standard STP mechanics, not RSTP. This is an interesting aspect of the PVST simulation mechanism. Even though switch 4 is running rapid PVST Plus, and MSTP uses rapid STP mechanics, connections between MST regions and PVST Plus switches use standard STP. In the lab video, we'll take a look at a packet capture, but what you'll see is that switch 2 and switch 3 will start sending standard STP BPDUs to switch 4, not rapid STP BPDUs. So because switch 4 receives standard STP BPDUs from switch 2 and switch 3, it identifies them as standard STP neighbors. Now let's see how the PVST simulation mechanism works. As you know, switches running PVST Plus run a unique STP instance for each VLAN, sending and or receiving unique BPDUs for each. But switches running MSTP only send and receive BPDUs in a single instance, MSTI 0. So for these switches to interact, the MSTP switches need to adapt. When an MSTP switch receives a PVST Plus BPDU on a port, it activates a backward compatibility mechanism called PVST simulation. So when switch 4 boots up, it declares itself the root bridge and sends PVST Plus BPDUs out of its ports. This causes switch 2 and switch 3 to activate PVST simulation on their G02 ports. And how does that work? When receiving BPDUs from a PVST Plus switch, the MSTP switch compares the PVST Plus VLAN 1 BPDU to MSTI 0. So switch 4 sent BPDUs in 50 different VLANs to switch 2 and switch 3, but the important one is the VLAN 1 BPDU. In this case, switch 4's priority in VLAN 1, 32768, is lower than switch 1's, 8192, so switch 4 does not become the CIST route. What about the BPDUs in other VLANs? They aren't totally ignored. They are used for some consistency checks that we will look at later, but they aren't used to determine the root bridge and the resulting STP topology. For that purpose, switch 2 and switch 3 only care about the VLAN 1 BPDU. So after an MSTP switch receives a PVST Plus BPDU, it activates the PVST simulation mechanism on the port. This causes switch 2 and switch 3 to start sending PVST Plus BPDUs to switch 4. As you know, MSTP switches normally send one BPDU for MSTI 0, and that's it. But switch 4, running PVST Plus, expects to receive BPDUs for every STP instance, for VLANs 1 to 50. To satisfy switch 4's requirements, switch 2 and switch 3 duplicate their MSTI 0 BPDU and send it in each VLAN necessary, so VLANs 1 to 50. The BPDU is sent using the classic STP format, as I mentioned before. We'll check that out in the lab video. And these BPDUs are sent with switch 2 and switch 3's own bridge IDs, not switch 1's. Unlike when interacting with another MST region, when interacting with a non-MSTP switch, they don't present the region as a single logical switch when they send BPDUs. However, they do indicate switch 1 as the root bridge in their BPDUs, of course. And then switch 4 accepts switch 1 as the root bridge. In the diagram, you can see each port's STP role. Because only MSTI 0 is used to interact with switches outside the region, each boundary port is either forwarding in all VLANs or discarding in all VLANs. And this necessitates a couple of rules about any PVST Plus switches bridge IDs that must be followed. These rules are what we'll cover next. First, if the CIST route is in an MST region, VLANs 2+, meaning any VLANs that aren't VLAN 1, must have a bridge ID inferior to the CIST route. This is the case in our example here. The CIST route is switch 1, and its MSTI 0 priority is 8192. Switch 4's priority in all VLANs is 32768 plus the VLAN ID, so its bridge ID is inferior to switch 1's in all VLANs. So it satisfies the rule. In the next slide, we'll see what happens if it violates the rule, and why the rule is necessary. The second rule is that if the CIST route is not in an MST region, so if switch 4 is the CIST route, VLANs 2 plus must have a bridge ID superior to VLAN 1. We'll cover that rule later, but first let's move on to analyze the first rule. So as you know, only the VLAN 1 BPDU is used to determine the role and state of the boundary ports. The ports will remain in the same state for all VLANs. This means that if the CIST route is in the MST region, and switch 4 claims itself as the route bridge for another VLAN, VLAN 2 or above, a loop can occur. Let's see how that works. I've modified switch 4's priority to 4098 in VLAN 2. This means that, in VLAN 2, it will declare itself the route bridge and make its G00 and G01 ports designated. And now we have a loop between switch 1, switch 2, switch 3, and switch 4. So this is why the rule exists. A loop has the potential to bring down the entire LAN, so this is obviously not a good situation. To avoid this, switch 2 and switch 3 check the VLAN 2 plus BPDUs to make sure they follow the rule. This is one of the consistency checks I mentioned earlier. Although only the VLAN 1 BPDU is used to determine the topology, the VLAN 2 plus BPDUs are still checked to make sure they follow this rule. So when switch 4 sends VLAN 2 BPDUs, claiming itself to be the route bridge, switch 2 G02 and switch 3 G02 enter the PVST simulation inconsistent state and are blocked. And remember, these ports have the same state in all VLANs, so this means that no traffic from switch 4 can enter the MST region now. All VLANs are blocked. Here you can see the syslog message that switch 2 shows when it receives the BPDU from switch 4. Blocking designated port G02, inconsistent superior PVST BPDU received on VLAN 2, claiming route, and then switch 4's bridge ID. And in the output of show spanning tree MST0, you can see that G02's status is broken. It's in the PVST simulation inconsistent state, blocking all traffic. To solve that, and let switch 2 and switch 3 G02 become active again, just increase switch 4's priority in VLAN 2 so it stops claiming itself as the route bridge. You'll get a message like this on switch 2 and switch 3. PVST simulation inconsistency cleared on port G02. And G02 is now forwarding again. Okay, that's the first rule when connecting PVST plus switches to MST regions. If the CIST route is in an MST region, PVST plus VLANs 2 and greater must have a bridge ID inferior to the CIST route. Now let's look at the second scenario and rule. This time, switch 4 is the CIST route. Its VLAN 1 priority is lower than the MSTP switch's MSTI0 priorities. However, notice that I configured its VLAN 1 priority higher than its priorities for VLANs 2 to 50. That's because of the second rule. If the CIST route is not in an MST region, PVST plus VLANs 2 and greater must have a bridge ID superior to VLAN 1. Before we examine why that rule is necessary, let me point out a few things. With switch 1 no longer the CIST route, it doesn't automatically become the CIST regional route for region 123. Instead, switch 2 becomes the new CIST regional route because switch 1 has no boundary ports. Switch 2's external route path cost is tied with switch 3, but switch 2 has a lower MSTI0 bridge ID. With switch 2 as the CIST regional route, switch 1 and switch 3 point their route ports toward switch 2. And then, switch 2 provides the region's connection to switch 4. One important thing to note is that for VLANs 2 plus to have a superior bridge ID to VLAN 1, their configured priority must be lower. This is because of the extended system ID. PVST plus adds the VLAN ID to the configured value. So if VLANs 1 to 50 are all configured with the same priority, VLAN 1 will have the lowest, and therefore superior, bridge ID, like this. Switch 1 has the lowest bridge ID, even though all VLANs have the same configured priority, 0. The point of this rule is to ensure that if the route bridge is in the PVST plus domain, it is so for all VLANs. The PVST simulation mechanism isn't flexible enough to support different port roles for different VLANs on the boundary ports. So to test it, I've returned switch 4's priority for VLANs 2 to 50 to the default. Let's see what happens. After receiving switch 4's inferior BPDUs in VLANs 2 to 50, switch 2 G02 should become a designated port for VLANs 2 to 50. But the superior VLAN 1 BPDU tells G02 to be a root port because it connects to the CIST route. So there's a conflict here, and switch 2 G02 moves to the PVST simulation inconsistent state until the conflict is resolved. As a side note, what about switch 3 G02? It doesn't get disabled because it already blocks all traffic. It's an alternate port in the discarding state. There's no need to block it. Okay, to repeat a point from earlier, PVST simulation doesn't allow for a separate role for each VLAN. Boundary ports are either root or master for all instances, designated for all instances, or alternate for all instances. Note that I joined the root and master roles together. That's because a master port effectively functions like a root port in the CST, leading toward the CIST route. So here are the results in the CLI of switch 2. Blocking root port G02, inconsistent inferior BPDU received on VLAN 2, claiming root, and then switch 4's bridge ID. And here's the output of show spanning tree MST0. G02 status is broken because it's PVST simulation inconsistent. And to show the master role, here's the output of show spanning tree MST1. Same thing, but the port role is master instead of root. To solve this, make sure that switch 4's bridge ID in VLANs 2 and greater is superior to VLAN 1. I returned switch 4's priority to 0 for VLANs 2 to 50, and a syslog message says the inconsistency has been cleared. As you can see, G02 is now forwarding again. Okay, let's review what we covered in this video before moving on to the quiz. We covered the topic of connecting MST regions to PVST Plus or Rapid PVST Plus domains, and the PVST simulation mechanism is what enables that. MSTP and PVST Plus are different protocols, different languages, so for the switches to communicate, the MSTP switches have to speak the same language as the PVST Plus switches. How it works depends on whether the CIST route is in an MST region or in the PVST Plus domain. Here's a summary of the key points we covered about the PVST simulation mechanism that Cisco switches running MSTP use. When receiving BPDUs from a PVST Plus switch, the MSTP switch maps the PVST Plus VLAN 1 BPDU to MSTI0. And when sending BPDUs to a PVST Plus switch, the MSTI0 BPDU is duplicated and sent in each VLAN necessary. So this interaction between MSTI0 and VLAN 1 is the key to the PVST simulation mechanism. Each MSTP boundary port is either forwarding in all VLANs or discarding in all VLANs. That's because its port roles are decided by a single MST instance, MSTI0, and this necessitates a couple of essential rules that must be followed. First, if the CIST route is in an MST region, PVST Plus VLANs 2 and greater must have a bridge ID inferior to the CIST route. Now, I didn't mention this, but what if there is no VLAN 1 in the PVST Plus domain? If VLAN 1 isn't present in the PVST Plus domain, meaning there is no VLAN 1 BPDU, the CIST route will be in the MST region, and the same rule applies. PVST Plus VLANs 2 and greater must have a bridge ID inferior to the CIST route. We'll test that in the lab video. And the second rule is if the CIST route is not in an MST region, PVST Plus VLANs 2 and greater must have a bridge ID superior to VLAN 1. Okay, now before finishing up, let's do a couple of quiz questions to test your understanding. Here's quiz question 1. Which of the following statements about a switch using the PVST simulation mechanism are true? Select 2. Pause the video now to think about the answers. Okay, the answers are C and D. C is correct because if an MSTP boundary port sends BPDUs to a PVST Plus switch, it duplicates the MSTI0 BPDU and sends it in each VLAN necessary, each VLAN for which it received a BPDU from the PVST Plus switch. D is correct because, to determine the PVST Plus switch's role in the CIST, The MSTP switch takes the VLAN 1 BPDU from the PVST plus switch and translates it to MSTI 0 in the MST region. A is incorrect because although BPDUs for VLANs 2 plus aren't used to determine the STP topology, they aren't totally ignored. They are used for consistency checks. And B is incorrect because of what I just explained for D and A. VLAN 1 BPDUs are translated to MSTI 0, but BPDUs for other VLANs are only used for consistency checks. They aren't translated to other MST instances. Okay, let's go to question 2. If the CIST route is in an MST region that is connected to a PVST plus switch, which of the following rules is in place to prevent loops? Pause the video now to think about the answer. Okay, the answer is C. The PVST plus switch's bridge ID in VLANs 2 plus must be inferior to the CIST route's bridge ID. If the CIST route is in an MST region, it means the PVST plus switch's bridge ID in VLAN 1 is inferior to the CIST route's bridge ID. To ensure consistency and avoid loops, the PVST plus switch's bridge ID in VLANs 2 and greater must also be inferior to the CIST route's. For review, here are those 2 rules we covered before. This question is asking about the first rule. Okay, that's all for the quiz and this video. I hope it was helpful. Thanks for watching. Before finishing this video, let me thank my JCNP level channel members who support me through YouTube channel membership. To become a member, please click the Join button under the video. Thanks to Jonathan Makara, Velva Jacob, George, Nasir Chowdhury, Gustavo Macedo, Marcel Lord, Dragos Hirnea, Zakib Shah, Mir Salman, Vitaus194, Mark Jackson, Bold1C1U, Gerald Guillaume, Fristas1207, Hector Hernandez, Arpad Conives, 5 Feet, Owad, Daniel Brown, Jose Alvarez, Hussein Yavuz, Samuel Tavares, Kevin Hayes, Roger Bratseth, Brian Grant, Georgi Gemejev, Cats for Life, Adelson Pereira, Farad69, Madmark50484, Alexandru Stratan, Hiago Bicalho, Lucian Stoichitoyu, DMJ2, Kurt Nell, Dear Diso, Steve Cox, Jasper Yim, Pedro Hartman, Tricky Mickey 123456, Ivano Capuano, Jefferson Steelflex, Toxic, Wilmer Romero, Sinan Sarisinar, Gio, Daniel Andrade, Mike Crumby, Dragos George, Jairo Francisco, Filip Jovanovic, Mateusz Zashinsky, Ruben Hernandez, Electro Jedi, Trevor Goldman, Gavin Paul Tech, Sunny Idigu, Jeffrey C., Chitsinde, Stephen White, Edificare, Fio Fiohain, Dimitro Lis, Ferris Al-Zaharani, Jean-Marcel Belmont, Mikhail Chapsky, Hemanth Jabalpuri, Dariush D., Juan Morales, Gonzalo Nicolas, Dune Sol, Christine Schubert, Julio Maya, Josie, Egreso, Komlan Kapedemi, Gökhan Doymaz, Hashem Rodef, Anand Abyankar, Clyde Mkorobindo, Adekola Ismail Salami, Orlando Flores, Ray Enriquez, Adrian Martinez, MD Danielwitz, Gabriel Afolabi, GG7 Rohan Surti, and Tobe Hedin. Sorry if I pronounced your name incorrectly, but thank you so much for your support. Thanks to you and my other supporters, I am able to make these videos and release them for free on YouTube, so I really appreciate the support. Another great way to support the channel is to like the video, leave a comment, subscribe, and most importantly, share this video with others. So if this video was helpful, I'd appreciate it if you did any of those. Thanks for watching.